Welcome to Reimagining Common High School Content webinar. My name is Elise Gomez, and I am a Connecticut Noyce Math Teacher Leader Fellow in New Britain Public Schools. Joining me to present today's content will be the following Connecticut Math Teacher Leader Fellows: Jen Downs of Manchester Public Schools, Carson Dunn of Hartford Public Schools, and Kate Grayup of Hartford Public Schools. And we are supported by Jillian Kavanaugh of University of Hartford. Thank you for joining us for the fifth installment of From Foundations to Futures, a PD series on readiness, access, and alignment. Today we'll be talking about common content for high school mathematics. This webinar is related to some ideas you've heard in other elements of this series, including post-secondary readiness and pathways.
So why should Connecticut reimagine what mathematics looks like in high school? Let's start with the big picture. For decades, the high school math sequence has followed the same narrow path: Algebra 1, geometry, then Algebra 2, with the intent to eventually reach calculus. But the reality is that this model no longer serves the majority of our students. According to the National Center for Education Statistics, in the 2021-2022 academic year, about 2 million bachelor's degrees were awarded nationwide. Of those, only 22% were in STEM fields. That means nearly 78% of students were not pursuing STEM degrees, yet our math sequence is still structured as if calculus is the universal end goal. The workforce also reinforces this point. The U.S. Bureau of Labor Statistics reports that there are 327 occupations that require only a high school diploma or equivalent, nearly double the number of occupations requiring any other level of education. This means many of our students are going straight into jobs where data literacy, quantitative reasoning, and problem solving are far more relevant than traditional calculus. We propose a vision of rigorous, modern math accessible to all students that will prepare them for whatever path they pursue after high school. When we look at outcomes specifically here in Connecticut, the disconnect becomes even clearer. In the EdSite graphic shown, you can see state SAT performance data for math over 3 consecutive years. In 22-23, only 34.1% of Connecticut students met the SAT benchmark for math. That fell to 29.5% in 23-24, and then rose slightly to just 31.1% last school year. For comparison, in reading during those same years, between 52% and 58% of students met the benchmark. So while more than half of our students are demonstrating literacy readiness, fewer than a third are showing readiness in math. It's worth considering. Is this gap really about student ability, or does it point to issues of access and relevance in how we're structuring math content? Too often, students repeat material from middle school or encounter topics that feel disconnected from their lives. That raises questions about whether our math offerings are truly engaging students and preparing them effectively for what comes next. Next, when we pair this with post-secondary enrollment data, the picture is even more clear. In 2023, 68.4% of graduates enrolled in a 4-year college in their first year. That leaves 31.4%, almost 1/3 of our students, not going directly to college. But we've been structuring our high school math curriculum as if every single student is on a calculus to college track. That might be a mismatch. We're preparing 100% of students for a single outcome when in reality, students take many different pathways, whether that's entering the workforce, pursuing certification programs, or choosing 2-year degrees. If we want math to serve all students, it has to prepare them with skills that are transferable: data literacy, quantitative reasoning, problem solving, not just a fast march to calculus. As we switch gears and start to explore what it is we will be recommending, it's important to understand the current expectations for a high school graduate in Connecticut. Instead of prescribing specific courses like Algebra 1 or Algebra 2, Connecticut currently requires students to take 9 credits of STEM-designated courses. On one hand, this gives districts flexibility, but on the other, it has created inconsistency. What counts as rigorous math may vary widely from one district to another. That means access isn't equal across the state. One student may get exposure to data science or statistics, while another student in a different district may only see a very traditional sequence. This is where our work connects to the broader movement.
Connecticut has just joined the Launch Years Initiative, a national effort led by the Dana Center at UT Austin. More than 20 other states are already doing this work, states like Rhode Island, Oregon, Ohio, Idaho, and Maryland. Each has already taken bold steps to modernize math. Rhode Island, for example, redefined Algebra 2 to align with real college expectations and cut out unnecessary content. Oregon and Ohio emphasized modeling, data, and reasoning. Maryland is restructuring entirely with an integrated approach. So Connecticut is not alone. We are part of a national movement to align high school math with both college and workforce needs. This gives us a chance to learn from other states' successes and to design a system that works for our students. So what does this mean for us here in Connecticut? Our vision is straightforward but ambitious. Every student should engage in rigorous mathematics that develops their ability to reason, model, and apply quantitative skills. Every student should see pathways that are relevant, whether they're aiming for STEM, business, health careers, or the skilled trades. And every district should have a consistent, coherent sequence that makes these opportunities possible. That starts with a modern Algebra 1, redesigned to eliminate repetition from middle school, fill gaps through concurrent support, and introduce content earlier that connects to data and technology. From there, students move on to geometry plus statistics, which highlights essential geometric reasoning while bringing in real-world data applications. Finally, we envision a flexible advanced algebra, a course that includes the core content needed for college readiness and accountability measures like the SAT, but offered in ways that connect to students' interests, data science, health STEM, economics, or quantitative reasoning. This approach balances consistency, so every student in Connecticut has access with flexibility, so districts can connect content to student goals. In short, our vision is about opening doors instead of closing them. Math should be an on-ramp to opportunity, not a gatekeeper.
We now offer a possible sequence of high school mathematics topics and how these major areas relate across the multiple years. Please note the arrow. We start with algebra and then move clockwise through the other domains. Our goal is a coherent, equitable pathway that builds procedural skill and conceptual fluency. We begin with algebra, which grounds students in equations, functions, and systems, the foundation for later work. Moving clockwise, every student completes one semester of statistics early in their sequence to ensure exposure to data analysis, distributions, and probability, skills that are directly useful for college and career readiness and helpful for standardized assessments. Next is geometry, focusing on spatial reasoning, shapes, and applications. Note that some specialized geometry content is shifted out of the full year core and made available as electives. Continuing clockwise, students engage with polynomial functions, emphasizing behavior and operations, and then with nonlinear systems, which includes quadratic, cubic, and radical equations, all building back into the algebraic reasoning students began with. The changes we've made are intentional by moving some niche geometry topics, for example, extensive Euclidean proofs and deep circle theorems, into elective offerings. We preserve rigor for students who need and want it while keeping the core pathway accessible and relevant for all. Requiring a semester of statistics ensures universal access to data literacy. These shifts increase opportunities for all students, reduce unnecessary redundancy, and align classroom experiences more closely with college and workforce expectations. For a full breakdown of the specific topics included in each domain, please follow the link on the slide. The key takeaway is simple. This model starts in algebra and proceeds clockwise to create a connected, flexible sequence that supports students' diverse post-secondary goals. On the previous slide, we showed the big picture structure of the proposed curriculum. This table provides a more detailed look at the specific topics within each course area. We won't go through every line right now, but the purpose of this slide is to give you a sense of the depth and breadth of what's included. You'll notice how the topics are sequenced to build logically from one course to the next, while also ensuring exposure to areas like data, probability, and polynomial behavior earlier than in the past. This level of detail is especially helpful for anyone who wants to dig deeper into how you might distribute content across courses. Remember that these types of changes would be made at the school or district level to intentionally restructure. The goal is not to cut content, but instead to locate it where it best supports student learning. There are many ways a school or district might approach this process of being intentional about how students get access to mathematical concepts. Traditionally, the mathematical concepts have been organized into something like the image on the left. Instead, a school or district might choose to distribute the mathematical concepts across courses more evenly, as shown on the right. What's important is that all students get access to critical mathematical ideas that they need to be successful.
On the previous 2 slides, we talked about important content standards, those that really matter for students' future success. Now let's look at what that could look like in practice. Here's an example pulled straight from the College Board SAT question bank. We have a simple system of equations, nothing too intimidating. Before jumping into solving, I want you to think about how you would approach this. What's your first instinct? Substitution, elimination, or maybe graphing? Now consider this. Modern technology can make this problem accessible to all students. With a graphing calculator or digital tool, students don't need advanced algebraic manipulation skills. They just need to be thoughtful about how to use technology to represent and interpret relationships. The key idea here isn't to test procedural algebra, but to recognize that with the right tools, every student can reason through and solve a problem like this. Here's what that same problem looks like when we use technology. In this case, Desmos, which is available to all students on the SATs. When both equations are entered, students can instantly see where the 2 lines intersect. That point of intersection represents the solution, the x and y values that satisfy both equations. What's powerful here is that the visual gives students immediate feedback and it builds conceptual understanding. They don't have to rely only on symbolic manipulation. They can see the relationships and verify their reasoning. This is a great example of how thoughtful use of technology doesn't replace mathematical thinking. It supports it. It helps make this kind of algebraic reasoning accessible to all students. So here's what it would look like if we solved that same system by hand. We'd have to isolate a variable, substitute, simplify, solve for the other variable, and finally check our work. Several steps, each with opportunities for small errors. It's methodical, but it's also time-consuming. Now, this isn't to say that we never teach these steps. They're important for building understanding, but the emphasis should shift. If all students can purposefully use technology, we can actually increase the rigor. Instead of getting stuck in the procedural drudgery, students can focus on interpreting what their answers mean, making connections, and applying their reasoning to more complex real-world situations. That's how technology becomes a tool for learning. It helps every student access higher-level mathematical thinking. Consider how your current math scope and sequence aligns with these recommendations. What challenges may arise and how your school could partner with local industry or higher education to prepare students for post-high school math opportunities. As you consider these ideas, there's more for you to explore in the available Fast Facts sheet and PD playlist.
Thank you for joining for the 5th installment of From Foundations to Futures, a PD series on readiness, access, and alignment. We look forward to you joining us at the next in the series, where you will have an opportunity to learn about mathematics in middle school and important considerations related to acceleration options.